All right, we're starting the next chapter now, chemical equilibrium. Now, we've discussed equilibrium before a little bit. Now we're really going to get deep into it. Let's start out with what is equilibrium. Well, let's take a look. Let's say you had a container of dinitrogen tetroxide. While it's cold, that's a colorless gas, and it'll exist in this container, has no color to it. However, if you heat this up to 200 degrees Celsius, we find that this dinitrogen tetroxide actually decomposes, forms 2 moles of nitrogen dioxide, and nitrogen dioxide is a brown gas. So, one would expect then, with the reactions we've been talking about before, that if we start with this cold colorless N2O4, heat it up, we'd end up with this container having dark brown nitrogen dioxide. But it turns out that's not the case. When you run it, you start out with the N2O4 heated up to 200 degrees, but as you wait for a while, it gets darker and brown, darker brown, darker brown, and it reaches this point right here. But it doesn't get as dark a brown as you'd expect it if it all got converted to nitrogen dioxide, because that didn't happen. It turns out this reaction here is an equilibrium reaction, meaning the forward reaction occurs, but the reverse reaction can also occur. Two NO2s can get together and form an N2O4 under these conditions. And so, since that reverse reaction is occurring, as a forward reaction occurs and forms more nitrogen dioxide, the reverse reaction occurs to form dinitrogen tetroxide, and the two meet somewhere in between these two extremes. And our whole chapter on equilibrium is to find out, okay, where are these going to meet? At what point does the reaction appear to stop, where the concentration of everything in solution does not change anymore? And when this occurs, note the two reactions kind of duke it out, and you end up with a mixture of both reactants here. And very importantly, when the concentrations of reactants and products have stopped changing, meaning the dinitrogen tetroxide, the concentration of it is remaining constant, and the concentration of nitrogen dioxide product is remaining constant. Once we've reached this spot, we are at equilibrium. Now, something very important, as we've discussed before, when you are at equilibrium, the concentrations of reactants and products have stopped changing, but the reactions are still going on. The dinitrogen tetroxide is still forming nitrogen dioxide. The nitrogen dioxide is still forming dinitrogen tetroxide. It's just at equilibrium, the forward rate of reaction equals the reverse rate of the reaction. And we've discussed that before in the last chapter. When the forward rate equals a reverse rate, we are at equilibrium. And to note it's an equilibrium reaction, we are going to use this special little arrows right here. N2O4 gas in equilibrium with two NO2 gases. And something to be aware of here is when you've reached equilibrium, it turns out the concentration of N2O4 will be the same no matter what you started with. Meaning, if you start with 100% N2O4 and get this reaction going, you will end up with this much brown color. If you started with 100% NO2, you will end up with the same brown color. This equilibrium position, how much N2O4 we have compared to how much NO2 we have, is the same whether you start with 100% N2O4 or 100% NO2. Okay. So the other thing to realize about these reactions is most likely the concentrations of your two reactants are the reactants and the products are not going to equal each other. Equilibrium does not mean the amount of reactant equals the amount of product. That's not what it means. Equilibrium means the concentrations have stopped changing. you might find you have a whole lot more NO2 than N2O4. Or who knows, you might find out you have a whole lot of N2O4 and not much NO2. Most likely at equilibrium, the two are not going to equal each other, though. And so graphically, we can look at it like this. It turns out for this reaction, if we start with N2O4, 1 molar, it turns out this reaction goes a lot of the way to making NO2, the product nitrogen dioxide. The equilibrium lies towards the right, we say. When we have this equation right here, our products are on the right, our reactants are on the left. It turns out this equilibrium lies towards the right. We have more product at equilibrium than we have reactant. If we look at it graphically, we see this. If we start with N2O4, pure N2O4, which means at the beginning of our reaction, we're looking at the concentration of reagents versus time. At the beginning of the reaction, we have no NO2. At the beginning of the reaction, we have 100% N2O4. It's all N2O4. Let's say this is 1 mole right here. As the reaction starts, the amount of N2O4 goes down. The amount of reactant N2O4 goes down as it is converted to the product NO2. Also, the concentration of NO2 goes up. Note this looks a little bit weird. The concentration of NO2 is actually going to get higher than the initial concentration of N2O4 because when we looked at our reaction, each N2O4, every 1 mole of N2O4 makes 2 moles of NO2. So if this reaction actually went 100% all the way, if it was not equilibrium, if we started with 1 molar N2O4, we would have had 2 molar NO2 at the end. But what we see here, graphically, if we start with our 1 molar N2O4, the concentration of N2O4 goes down, but it doesn't reach 0. It levels out at this value, this concentration of N2O4. Concentration of NO2 does not go up to 2 molar. It's going to level off at this value, and that's what the graph would look like if we started with pure N2O4. What if we did the opposite? We just looked at starting with pure N2O4 to get to this spot. What would happen if we started with pure NO2 to get to this spot? 2 molar NO2 to get to the equilibrium concentrations. What we'd find, we had mainly NO2 at the beginning, and its concentration would go down a little bit. The N2O4's concentration would go up a little bit, start with 0, go up a little bit. But note, at equilibrium, whether you start with NO2 or start with N2O4, you're going to still end up with this amount of NO2 at equilibrium and this low amount of N2O4 at equilibrium. All right, and we've already discussed that. Okay, well, how much are we going to get? How do you know if the reaction lies to the left or to the right? Well, that comes via the equilibrium constant. And yay, we get to do more math. And truthfully, the math gets a little bit hairy at times. We'll find a way to try to cut some of that hairiness, but it's going to get interesting. First thing we need to look at now is the equilibrium constant, given the symbol capital K. Recall the rate constant is a lowercase k. Equilibrium constant is the capital uppercase K. For the general reaction, A moles of A plus B moles of B in equilibrium with C moles of C plus D moles of D, we can define the equilibrium constant as the concentration of C to the little c power times concentration of D to the little d power divided by the concentration of A to the little a power, concentration of B to the little b power. With equilibrium constants, you plug in those stoichiometric numbers. That stoichiometry is there, and it is the exponents in equilibrium constants. A few things to keep in mind. Equilibrium constant, products over reactants. Keep that in mind. When you have the reaction, it's products, C and D, over reactants, A and B. This right here is called the equilibrium constant expression. The old school name for it is the law of mass action. Okay. So, knowing this, if we had this reaction right here that we've been looking at, N2O4 gas in equilibrium with 2NO2 gas, what would be the equilibrium constant expression? Well, the equilibrium constant expression, products over reactants raised to their stoichiometric powers. That'd be K equals, note the equilibrium constant expression is K equals concentration of NO2 to the second power divided by the concentration of N2O4 to the first power. Anything to the first power, we don't have to write a little one there. And so that's what it is. What about for the reaction N1N2 plus 3H2 in equilibrium with 2NH3? Well, it's a products over reactants. The equilibrium constant expression is K equals concentration of NH3 to the second power divided by the concentration of N2 times the concentration of H2 to the third power. There's the equilibrium constant expressions. All right. How hard is that? Well, we're going to get to that. First thing to note, let's look at the magnitude of K, because we're going to be calculating numbers. We're going to get the number, the actual numerical value of K. And what does it mean if the numerical value of K is much greater than 1? Well, if K is greater than 1, that means the numerator is larger than the denominator. Since the numerator is always the products, if K is greater than 1, that means our concentration of products is much larger than our concentration of reactants. We say that reaction lies to the right towards products. What if K is much less than 1? Well, if K is much less than 1, that means the denominator is larger than the numerator. We have much more reactants here. We have much more reactants than we have product. We say the equilibrium lies to the left. What if K is about 1? If K is close to 1, we have really a decent mixture of products and reactants. We have a decent amount of product and a decent amount of reactants, not necessarily 50-50.